Hello! This video is about the 9 common techniques for rewriting integrands so that our basic antidifferentiation rules apply, and this is our second technique. It's called separating the numerator. Here's an example of a problem where we might want to separate the numerator. So I'm going to start with an easy example. Okay, this is a clear case when I would separate the numerator because, first of all, my basic rules don't apply. My basic antidifferentiation rules list does not have a rule for the antiderivative of a quotient, and I've got a quotient here. And there's so many Calc 2 students coming straight out of Calc 1 that really want to apply the quotient rule in this case. Don't do it. We're taking antiderivatives, not derivatives, and our basic rules just don't apply. The next possibility would be a u substitution, but here there's really not a clear choice for u. I could let u equal maybe the square root of x. I could write that in terms of u, I could write that in terms of u, but the derivative of the square root of x ends up with a 1/2 x to the negative 1/2 times dx. Like, that's a possibility, but it's still not the most straightforward way to do this. So yeah, basic rules don't apply. U sub might work, but it isn't the most straightforward way to do this. So we are going to do what's called separating the numerator. And here's the basic idea. Whenever you're adding fractions, let's say you've got 1/5 and 3/5. If you think all the way back to grade school, this 1/5 is like parts of a whole. Like, you might think of a pie, and you might think of 1/5 of a pie. That pie has been split into 5 equal pieces. I was going to try to draw a pie for you and split it into 5 equal pieces, but it's actually pretty hard. Yeah, something like that, but those aren't equal. But you get the idea. Each of these pieces is supposed to be equal, and then it would be separated into fifths. If I've got 1/5 and then I'm adding 3/5 of a pie, well, how many pieces of a pie do I have? Well, since each fifth is exactly the same size, all I have to do is add the 1 and the 3, and that's how many fifths I have. So the denominators are the same. We keep the common denominator and just add the numerators, and so we get 4/5. You guys are in Calc 2, that's pretty easy and very straightforward. But the idea applies in general, even when we're not dealing with integers. So let's say you have a constant over c plus a constant over c, and you want to add these together. Well, the denominators are the same. So we keep the common denominator and we add the numerators. Most of the time when you're in grade school, you're in elementary school, or you're maybe even in a pre-algebra class, whenever you're adding fractions or rational functions or anything like that, if you have a common denominator, you're going in this direction. But it turns out you can also go in this direction as well. That's what we're going to do here. If I have a sum of terms and all of them are divided by one thing, I can take each term separately and divide it by that one thing. That's what this says. A plus b over c is the same as just taking a over c and b over c and adding them together. Sometimes my students in class will see I'll do this plus this, and then I'm adding them together. Now this has 3 terms instead of 2, but of course the principle is exactly the same. So I'm going to take my x cubed and divide it by 3 times the square root of x. And then I'll have the negative 2 times the square root of x and divide it by 3 times the square root of x. And the negative 4 over 3 times the square root of x. And I'm just taking each of these guys separately and I'm dividing them by that 3 times the square root of x. Now at this point, we still don't have a basic rule that applies, but with just a little bit of algebra and some exponent properties, we can simplify this and our basic rules will apply. First of all, I notice that the square roots of x reduce, which is really nice. That makes it just a constant term, which is very easy to anti-differentiate. And then these two guys need to be simplified in 2 ways. First, I need to pull out the constant, and then I also need to simplify the x to the 3rd power divided by the square root of x, and then the square root of x that's in the denominator. I need to rewrite that so that one of my rules applies as well. So let's talk about just factoring out the constants first, and then we'll deal with the square root and simplifying that. So first thing I want to do in order to get the right answer here is I want to factor out the constant. Now a lot of students will look at this and think that they're going to factor out a 3. And they're close, but they're not quite right because that 3 is in the denominator. You have to remember that there's an implied 1 up here. With that implied 1 there, I can see that the constant multiplying my x to some power divided by my x to a different power is that 1 over 3. There's a 1/3 there. It's sort of hiding, but it's a 1/3. So I'm going to factor that out or bring that down. I'm not bringing it outside of my integral because that 1/3 is just for this term and not for the other 2 terms. It needs to stay inside the integral. And I'm thinking of that as 1/3 times x cubed over the square root of x. Now I can also simplify the square root of x. May have been a while since algebra, but there is a rule that says if I have the nth root of x to the m, that's x to this power, m, divided by this power, the index of the root that goes in the denominator in the exponent. So if I had, let's say, the cube root of x squared, that's x to the 2/3. So I do that divided by that. Or the 5th root of x to the 4th, well, that's x to the 4/5, and so on. Now, if I just happen to have like the 6th root of x, that's a little bit less clear. But remember, if you have a variable that's just sitting there, that's just an x, that's the same as x to the 1st. So that's an x to the 1st power, and I can rewrite that as x to this power over that power. So this is x to the 1/6. In general, if that's an nth root, you're going to have x to the 1 over n. And whatever that number is there, that's the number in the denominator there. Now square roots are a little different. Just like there's an implied 1 there when there's an x, with a square root there's always an implied 2 on the index. 3rd root, 4th root, 5th root, any other root we have, they're going to have to tell you the index of the root. But with a square root, they don't tell you. It's just assumed that there's a 2 there. So this is actually x to the 3/2 power. And for our square root of x, that's combining just these 2 cases. You've got an implied 1 and an implied 2, so that's going to be x to the 1/2, or x to the 1/2 power. So that goes here. And we're going to use exponent properties to simplify that in a little bit so we can use our basic rules. Then I have a minus 2/3 in the middle. And then over here, I want to write this as a fraction times something involving powers of x, or a constant times something involving powers of x. In order to do that, first I'm going to factor out my constant. This one's really nice. That one had an implied 1, so there was a 1/3 I had to factor out. This one's nice because nothing is implied. I've got a 4 in the numerator, a 3 in the denominator, so there is a 4/3 out front. Now, I'm going to add a 1, or add a placeholder of a 1, excuse me, in order to make this equivalent to this up here. And a lot of students wonder why on earth I did that. Well, the reason why I did that is because I wanted to see this 1 over x to some power so that I could use my exponent properties to simplify it. Now, if you don't believe me, if you're like, where did that 1 come from? There was a 4, thought if there was no 4, there would just be an x to the 1/2. You're right, there is an x to the 1/2 in the denominator, but there needs to be that 1 as a placeholder. If I multiply this straight across, I get 4 times 1 is 4, and 3 times x to the 1/2 is the same as 3 times the square root of x. That works, that's the same as that. So I'm keeping that 1 there as a placeholder so that I can use exponent properties to simplify this guy and use exponent properties to simplify this guy. So we talked about this exponent rule. Here's another one. My computer's in the way, there we go. If you've got x to some power divided by x to a different power, you've got to subtract the exponents. Do n minus m. And that's what we're going to do over here. And then another rule that comes up often is 1 over x to some power. That's x to the same power, but negative if you bring it up to the numerator. So this is actually an x to the negative 1/2. Now if I subtract exponents here, it's 3 minus 1/2. That's x to the 2.5. We usually don't like to use decimals here for some reason. But this is, I can think of 3 as 6 halves. 6 divided by 2 is 3. So 6 halves minus 1/2 is 5 halves. And now I've pretty much rewritten everything. So I've got 1/3 times x to the 5 halves minus 2/3 minus 4/3 times x to the negative 1/2 dx. And now I've got a rule for that and a rule for that and a rule for that. One other thing that you should know, it's not appropriate for this problem, but it's going to be helpful on other problems. When you look at your antidifferentiation rules, you've got one rule for x to the n. And it says you should add 1 to the exponent and divide by the new exponent, and then add c. This works almost all of the time. There's only one time, only one value of n when this doesn't work. If n is -1, see what would happen? I have a -1 plus 1 is 0. I'd be dividing by 0. That would be a very bad thing. So this is for n not equal to -1. If n's not equal to -1, if n is any other power, we can do this, and that's what we're going to apply here and here. But if n is -1, well, that's the same as 1 over x in that case. And then we get natural log of the absolute value of x plus c. So what you'll see me do as I go through the example problems is you'll see me rewriting quotients, products involving powers of x as x to some power in every case except for when that power would be -1. If that power would be -1, I'm going to leave it as 1 over x so that it looks just like this rule. It's not applicable to this problem, but it might come up later, and it'll definitely come up later in this course. So now we are ready to apply our basic rules. I've got a constant times x to some power, so I'll apply the power rule. Bring your constant down. Then add 1 to the exponent. 5 halves plus 1 is 5 halves plus 2 halves, so 1 is 2 over 2. 5 halves plus 2 halves is 7 halves. And then you want to divide by the new exponent. Rather than dividing by 7 over 2, remember, dividing by a fraction is multiplying by the reciprocal. I'm just going to skip that step, and I'm going to multiply by the reciprocal, so I have a 2 over 7 there. Flip it and multiply. The antiderivative of a constant is a constant times your variable, whatever variable you're integrating with respect to. This is an antiderivative with respect to x, so we're going to get this constant times x. And then we bring our constant 4/3 down, add 1 to the exponent. A 1 plus -1/2 is positive 1/2. And then divide by the new exponent. Dividing by 1/2 is the same as multiplying by 2 over 1. Flip it and multiply. And that's your answer. It's not simplified, but that's your answer. So we're going to simplify. Multiply straight across. You get 2 over 21, x to the 7 halves. Minus 2/3 x. Multiply straight across. You have minus 8 over 3 x to the 1/2. I think I want to write that as the square root plus c. You could write that as the square root of x to the 7th as well if you want, but I think I'm just going to leave it alone. So that's how we handle that. So we've used a little bit of exponent properties. Those come up again and again in calculus class, especially when we get into sequences and series and we're trying to simplify quotients for what's called the ratio test. Like all of this is coming back. So that's built into our review of antidifferentiation. But how did we start this? We saw this was a quotient with 1, 2, 3 terms, and I had a monomial in the denominator. I don't have a rule for this, but if I take each of these terms separately and divide them by the 3 times the square root of x, I do have a rule for that and for that and for that. And so by separating the numerator and doing a little bit of algebra, we were able to apply this rule. Now here's another time when I might separate the numerator. This one is a little bit less obvious. But I will give you a good rationale, a reason why we would know to separate the numerator. So let's say you've got the antiderivative of 4x minus 5 all divided by the square root of 9 minus x squared dx. Now that looks like one of my basic rules. It also looks like a u sub, and because of that, because it looks like both, students tend to find this problem very confusing. Here is the rule that it looks most like from my list of rules. Let's say that 4x wasn't there. I've got that negative 5, or a constant, over the square root of a constant minus x squared. That looks a lot like this rule. And according to our table, according to our list of basic rules, this is the arc sine, or the inverse sine of x divided by a plus c. And if that was just a 5, I could do that. It would be an arc sine. Now, if that 5 wasn't there, you guys see how you might handle that? It's not a basic rule, but u sub would work for this. Do you guys see why u sub would work? With u substitution, remember, you're looking for a function nested inside of another function. And when you take the derivative of that function, don't worry about the constants. Like the derivative, like the part that involves x, the variable part of the derivative, it needs to be up here somewhere. It needs to be a part of the integrand as a factor. And the derivative of x squared has an x in it. And there's an x right there. So I know that a u sub would work for that. But for this, I can't do it. If I try to do the u sub here, let's say I tried to do the u sub. Use my inside function, that's 9 minus x squared. Du is the derivative of that times dx. Derivative of 9 is 0. Derivative of negative x squared is negative 2x. Don't forget your dx. The u sub doesn't work because I need a constant times the negative 2x dx up here somewhere. And I can always divide or multiply by something to get rid of the negative 2. I just need an x dx. There's an x and a dx, but that extra 5, it doesn't work with my u sub. I can't multiply this by something and get a constant times x plus or minus this extra 5. So the u sub won't work in its current form. But if I separate the numerator, if I write this as 4x over all of that minus 5 over all of that. So it looks like this. Now I've got a u sub, that'll work. And I think I'm going to factor out that negative 5. And then this guy looks like an arc sine. So I have a rule for that and I have a rule for that, but only after I separate the numerator. Be very careful about this, guys. A lot of students on the test over this material, when they see similar problems, will try to do a u sub unsuccessfully because they don't separate it. Like they might try to do the u sub and then say that this 4x minus 5 dx is equal to like negative 2 times du or something like that. It doesn't work because the 5 isn't accounted for. Or they might somehow say it's an arc sine. In both cases, the student is wrong, but they're also partially right because part of the answer is an arc sine and part of the answer is a u sub. But to get the whole answer, you need to separate that numerator and you need to do both. So we're going to do the u sub over here and then we'll do the arc sine over there. So I'm going to use this u. I have u equals 9 minus x squared, du equals negative 2x dx. And then I ask myself, well, what do I have to multiply this negative 2 by, this negative 2x dx by, so that I get the 4x dx that's in my numerator? Well, I could just multiply both sides by negative 2, and that would work. So negative 2 du is negative 2 times negative 2, which is 4x dx. So I'm just going to replace this 4x dx by this negative 2 du. Instead of writing 4x dx, I'm going to write negative 2 times du. And it turns out from this line, they're exactly the same thing. Now in the denominator, be careful, it's not just a u. 9 minus x squared is my u. This is my u. A lot of students will put a u there and then tell me it's a natural log, but it's not. Do you see the problem? Do you see what we didn't account for? The 4x dx is the negative 2 du. That's a u, but it's under the radical. The radical still needs to be there. You are literally replacing everything with something else that's equivalent to it in terms of u. And now that I've done my literal replacement, well, with a little bit more algebra, I'll be able to write this in a different way so that my basic rules will apply. So we're almost there. This is entirely written in terms of u, and I'm 2 steps from getting the right answer. So first I think I'll take out the negative 2, and then write this as 1 over u. But remember that square root is a 1/2 power. It's u to this power over, or this number over that number. And I'm going to come back to this in a little bit, and we're going to do the arc sine on that side. But for right now, we're here. And I still don't have a rule for that. Don't tell me it's natural log of u, or the absolute value of u to the 1/2. If that exponent is anything other than a 1, if that's not a 1 over u, but if it's 1 over u to some power, if it's anything other than a 1, it's not a natural log. You've got to bring that up to the numerator and use your power rule. If it is just a u, that is a log. But the 1/2, it's not. So we bring that up to the numerator. Remember, it's going to be u to the same power, but when you bring it up to the numerator, the exponent becomes negative. And I've got a du over here. And now I'm ready to apply my basic rule. Add 1 to the exponent. Negative 1/2 plus 1 is 1/2. My u's still there. Then I divide by the new exponent. Dividing by a fraction is multiplying by the reciprocal. So I'm going to multiply by 2 over 1. I'm just going to add an implied 1 right there. Maybe that's overkill. Now there's going to be a plus c. I'm just going to let the second integral take care of the plus c. When I simplify, I've got a negative 4 out front and a u to the 1/2. A 1/2 power is the same as a square root, so I'm going to write it as a square root, and then I'm going to plug u back in. Because remember, our goal is to find a function that we can take the derivative of that will give us this. This is an antiderivative. My function and my answer better have an x in it, because when I take the derivative of something with an x in it, I'm going to get something with an x in it, like right up here. This one with the u in it, it's never going to give me this function. So I need to back substitute. What was u again? That was 9 minus x squared, so I'm going to put that back in. So I'm done with that part. All right, second column. Here I'm looking at this, and I'm looking at this, and I'm pattern matching. This is a constant squared minus x squared. The order is very important. If that was an x squared minus 9, I could not do this. Excuse me. But since it's a 9 minus x squared, it fits exactly. A squared, that's the constant part. That's 9. So that means that a is the square root of 9, which is 3. We're always going to take the positive square root. Now, according to that rule, the antiderivative is just arc sine. Oops, actually I'm going to do it over here. You still have your negative 5, bring that down, times arc sine of x over a plus c, and a is 3. And then I'm going to bring that down here on my paper. Instead of adding, I'm just going to subtract 5 times the arc sine of x over 3. And add c. Sorry about that weird little dot. It shouldn't be there. If I had white out, I'd white it out for you. Don't forget to put 3 in. That's our answer. But that was just an example of us separating the numerator. So when I see something like this, if u sub doesn't work because of the extra constant, or the arc sine doesn't work because of the x, then what you've got is you've got two terms. You've got one with a u sub and one with the constant. So we separated the numerator here so that one of our basic rules would apply. Now, remember, if this is truly the antiderivative, if I take the derivative of this and I simplify, it should look like that. Just to practice our differentiation rules, and just to make sure to confirm that our answer is correct, let's take the derivative of this answer and show that we get the original integrand. So let's say I'm taking the derivative of this guy, and remember, when you're taking derivatives, it's better to write x, this square root of some function as a power. So we're going to rewrite it. This is negative 4 times 9 minus x squared to the positive 1/2, because there's an implied 1 there and an implied 2 there, minus 5 times the arc sine of x over 3 plus c. And after simplifying this derivative, we should get the original integrand back. Now remember how this works. When I'm taking the derivative of this sum or difference of 3 terms, I've got this minus this plus c. I'm going to take the derivative of this guy and then subtract the derivative of this guy and then add the derivative of this person. It's a c. You know what I mean. Personifying all of my functions here. But all of these guys I have to take the derivative of. I'm taking the derivative term by term. Derivative of the sum is the sum of the derivatives. Now, I might also need to remember a couple of rules from Calc 1. Don't forget the chain rule. If you're taking the derivative of f of g of x, I'm going to use 2 colors because it makes it a little bit easier to see. I take the derivative of the outside function first. Whatever's on the outside, I take its derivative. I put the inside function back inside. I don't do anything with it. Just plug it back in. And then I multiply by the derivative of the inside. We're going to need that anytime we try to take the derivative of a composite function. So anytime you see a function nested inside another function, that requires the chain rule. And also, you should know that if it requires the chain rule to take the derivative like it did on this one, when you go backwards, you're going to have to do u sub to do the antiderivative. U sub is just the chain rule in reverse. Okay, so we need the chain rule for that guy. We also need to know the power rule. Just helps to remind ourselves when we're differentiating, we bring the power down, multiply by x to the 1 less power. And then this arc sine rule. You may have forgotten it from Calc 1. Many people do. It's okay. Just got to refresh. The derivative of arc sine of x is 1 over the square root of 1 minus x squared. And that was derived back in Calc 1. Now, if there's something other than an x inside, we're going to have to use this rule combined with the chain rule in order to take our derivative. And we've got something other than an x up here. So we're going to need these guys in order to evaluate this derivative. Okay, so we're going to take derivative term by term. First guy, I'm sorry about the personification, I can't help it. I could help it, I choose not to. So I've got this negative 4 times a function to the 1/2 power. I know I have to use the chain rule because I've got a function inside another function. This is my inside function. I cannot simply take the square root of the 9 and the x. That is not 3 minus x. A lot of students want to write that square root of 9 as 3 square root of x squared is x. Not the same thing. It's just not legal. You could plug in some numbers and prove it. I'm not going to prove it right now, but you can't just take the square root of each term. So I'm going to have to use the chain rule. I've got negative 4 times a function to the 1/2 power. According to the chain rule, I take the derivative of the outside function first. Derivative of the outside is negative 4 times, bring that 1/2 down, inside function to the 1/2 minus 1, that's negative 1/2. Times the derivative of the inside by the chain rule. And derivative of 9 minus x squared is just negative 2x. So you can leave that on that line, or you can just work it out later, that's fine. So that's the derivative of the first term. And then we're going to subtract 5 times the derivative of the second term. Now this also requires the chain rule because I've got this x over 3 inside. The derivative of arcsine of some function, according to my arcsine rule right here, is 1 over the square root of 1 minus that function squared. Oops, I wrote cubed. Squared. And my function is x over 3, so plug it back in, times the derivative of the inside. Now, this, you absolutely do not have to use the quotient rule. That's just a constant times x. So many students I'll see when I'm grading their work, they'll use the quotient rule there, and it's good. That means that you really know how to do the quotient rule, and you're trained. Every time you see that fraction, you want to apply the quotient rule. That's great. But there's a much, much simpler way. Factor out the constant first. Remember, there's an implied 1 there. So there's an implied 1 over 3, that's a 1/3 x. And the derivative of a constant times x is just the constant, so we have a 1/3 right there. So that's the derivative of the second term. And then, of course, the derivative of the constant. What's the slope of a line y equals c? It's just 0. Derivative of a constant is 0. So that's our answer. Doesn't look anything like our original integrand, but our hope is that with a little bit of algebra, we can show that it's exactly the same as our original integrand. So I'm going to simplify a bit. Negative 4 times 1/2 is negative 2 times the negative 2x. And then I've got 9 minus x squared, whoops, to the negative 1/2 there. And then I've got a minus 5 over the square root of this. Now I've got 1 minus, if you've got a fraction squared, remember, anytime you've got a over b raised to the n, you can apply that n to everything inside. So if I've got x over 3 squared, that's the same as x squared over 3 squared, which is 9. And we're taking all of that, and we're multiplying it by 3. Or excuse me, not 3, 1/3. And that's our answer. It's still not simplified. Now you might say, oh, that's kind of ugly. I've got this weird fraction within a fraction over here. I might want to get rid of it. One way that you can get rid of it, and this is not intuitive, it's intuitive for me because I've done enough algebra that it's intuitive for me, but it might not be 100% clear that you might want to do this. One way that I can get rid of that 9 is I can distribute this 3 in. I can distribute this 3 to both terms in here, but I can only do that if I write this 3 under a radical. You might be saying, oh, there's no radical there, you can't just introduce a radical, and you'd be absolutely right, I can't. But if I want a radical to be there, I can do that as long as I also square the 3. Because the square root of 3 squared is just 3. Totally legal, totally legal. And now I can use this fact from algebra. Square root of a times the square root of b is just the square root of a times b. So I can put all of that under one square root, and I can distribute this 9 through. And when I distribute that 9 through, I'm going to get rid of that fraction that I didn't want. So we're going to be able to clean that up a bit. We should also clean this up a bit. I've got negative 2 times negative 2x is positive 4x. Negative times negative is a positive. And over here, I've got a 9 minus x squared. It's to the negative 1/2 power. So that's a 9 minus x squared to the positive 1/2 in the denominator. And remember, positive 1/2 power is the square root. That's looking pretty good. It's looking very similar to what I've got over here. Now I'm going to apply this property. Square root of a times square root of b is square root of ab here. Got 1 minus x squared over 9. And I'm going to distribute that 9. I know it's a little strange distributing on the right, but it's just as legal as distributing on the left. And distribute that 9 to both of these terms. Nine times 1 is just 9. And this x squared over 9 times the 9, the 9's are going to cancel, and we're just going to have a negative x squared. Ah, now I've got two fractions. Same denominator. If I want to subtract two fractions with the same denominator, I just subtract the numerators. Keep the common denominator. Hey, that's awesome. That's our original integrand. That's good. Because it means when I take the derivative of, when I take the derivative of this, I get this. So when I take the antiderivative of this, I should get this, and I did. So that works out.